This is looking at the back of the Heidenhain main controller, and you can see that the wiring in it is a little bit of a bird's nest. It's a lot better than it was when I got it, but when you've got inputs like this with all these multi-core cables of all different sizes and different wire gauges for the cores in each one, when you get up here, the cable management on the back of the machine is not great, so you end up with this kind of mess. These outputs on the back of this machine, of the Heidenhain, are all floating, and they're powered by a remote 24 volt DC power supply, and it powers this isolated backplane, optically isolated backplane. And similarly on the other PLCs, they've got floating outputs and inputs, and they're on the same 24 volt power supply. One area of interest is it has the ability to put up coded outputs on these terminals here, J22 down to J29. That 8-bit or byte output allows 256 coded outputs, but in fact the Heidenhain can only recognize 100 of them, and you can use it for multiple different things, and depending on what you're using it for, it has 3 strobes down here, an S and a T and an M strobe, which are the speed, the tool, and the machine codes for running the thing. So depending which of these, so you put a binary number on the back here, and then when that's set by the program, one of these 3 strobes will go off, and the receiving device will know which type of code it's reading. Because I don't have a tool changer on this machine, it never uses the tool strobe, and it never uses program 0 to give you all of the tool settings. So you can set it up so you set the radius and length and tool number in program 0. If you set it up to read that, it will ignore any tool data you put into any program that you run. So that's not invoked, and tool 0, program 0 is never used. The consequence of that is that every program you write has to have all of the tool information put into each individual program. It suits me because I only have 4 tool holders, and I set different tools into them all the time, which you wouldn't do if you had a tool caddy. All the outputs on this backplane are momentary. So some of them are hardwired, say to the MO3 for spindle start is hardwired to its relay. But you have to have in the relay logic an interlock that latches it on, because that signal from the Heidenhain will disappear. That means you also have to have another output from the Heidenhain which disables the latch. So for an MO3 you typically would send an MO5 to switch it off. The next thing is we have these 8 cores here on the bit setting are hardwired down here to this Izumi, to these inputs here. See here, bits 1 to 8 on this Izumi PLC, which does the gear changes or the speed changes. So when it does that, a function runs and changes the gear, which I'll show in another video. When that's finished, it sends back here, from here, auxiliary function finished, flashes this strobe, which is an output from here, and is input back up here on the backplane of the Heidenhain again, and that tells the Heidenhain that the auxiliary function is finished and that the program which has been halted can now proceed with the machine in the correct gear. In fact, then it'll probably do a star delta start MO3, and the Izumi again will decide on what the appropriate delay on the star delta timer is. In that case, it will again read these 8 inputs, but instead of using the S strobe, or being told by the Heidenhain to use the S strobe, the Heidenhain will instruct it to use the M strobe, which will invoke a different program in here to run the time delays on the star delta. And when the motor, that time delay is over and the motor is pulled into delta, it senses it here on the coils. These are the forward and backward coils for the spindle motor commands. And again, it'll run this auxiliary function to send it back to the Heidenhain and say, okay, now you can start milling.